Okay, so in this activity, you're coming along here, and you've got a curve in the plane. Let's see, make that a little bigger there. Shoot. All right, that's good. I'm not sharing my screen. Let's see. Okay, can you see your homework here and my cursor moving around?
Yeah.
Very good. Okay, so here we go. So you've got some curve, and this is not the curve in question, but I'm just going to make up a new curve like this. So maybe the curve is like this, something like that. And then say the curve is oriented this way for increasing time. All right, and so suppose we have this point right here, and that's for, say, t equals 4. This is not the situation in your problem, but I just want to do a similar situation. And one thing you're asked to find is t of 1 and n of 1. So I'm going to talk about t of 4 in my example and n of 4. You'll have a different curve, and you're doing it for time equals 1. So t of 4, if the orientation is this way, is something like this. Right? It's the direction of motion at that moment. So there's t of 4. And so what I want to tell you is that n, we talked about n of t being this formula where you take the unit tangent function and you take the derivative of it and then you unitize that. Okay, this is usually awful algebraically. This is a mess. It just goes on and on to do this and gets really big. You're bound to make mistakes. Because you're in R2, you do not need to do this. So we want to avoid this. This is just too much messy algebra. So we want to avoid this. And the way we can do that in R2 is to suppose this t of 4 was, say it's positive 4 over radical 17 and negative 1 over radical 17, right? Because it's to the right and down. To the right is positive x, down is negative y. And so we know that the normal direction of the normal vector is the direction of turning, and it's orthogonal to t. So it's along this. So there's two possibilities for n. It would be kind of this up-ish direction or this down-ish direction. So based on the curve, what would be the direction of n? Would it be exhibit A or exhibit B?
Down.
Yeah, it'd be this one, right? Because why? Because we're turning right. If we're on this object, we'd be turning right, and n shows the direction of turning. So that would be n of 4. Okay, so in R2, knowing what t is, we can just kind of write down what n is because we know they're orthogonal, right? And so t has the kind of the long x-coordinate and the short y-coordinate, and since these are orthogonal, so now n has that short x-coordinate and the long y-coordinate. And because they're orthogonal in the plane, those two are just flipped, right? We have the same proportion of changes, but they're just flipped. And then we just need to include either the plus or minus according to which way n points. So we can just write it down. What will the x component of n of 4 be? It'd be this right here, which is the same as this right here. So what's the x component of n of 4?
Negative 1 over the square root of 17.
Right, and it's negative not because this one was negative, so we get the magnitude, 1 over radical 17. And it's not negative because this one's negative. It's negative because why? We're going to the left. Right. Or left, correct. We're going to the left, correct. All right, now what about this magnitude? So the magnitude of the y component of n is? So do you see it's just the same vector as t, same proportion of changes, but just rotated 90 degrees. Therefore the y component would be?
Negative 4 over rad 17.
Yeah, it'd be 4 over rad 17, and then we have to say, is it up or down? Since it's down, it's negative. So that's a lot easier way. Given a t vector in R2, it's a lot easier way of just writing down the n vector rather than trying to do this, which we want to avoid at all costs. Okay, questions on that? So that's just a tip to help you with this one and to save you a lot of grief, okay? And then later on, I think it's, yeah, so the next question here, you're going to be finding the tangential component of acceleration and the normal component of acceleration as real valued functions. So it gave you formulas for that. And so for the formula for the normal component of acceleration was the magnitude of the cross product. But a cross product requires R3 vectors, not R2. So what you can do is just throw a 0 in your z component. And then you've got, so because that's true, everything in the z direction is 0 if you're in the xy plane. So just throw a 0 in your z components. Now you can take that cross product and take the magnitude of it. This is not AT, sorry. This is referring to this down here. Okay, so
Professor,
yes?
for A of t on that problem, we would just use the normal equation with the dot product.
Right, dot product doesn't require, that just works just as good in R2 as this R3. So there's no adjustment you need to make to the AT function. Because dot product you can just do the dot product of your vectors. But it's when you get to cross product that requires R3 vectors, you can just throw zeros in for z. Okay, so any comments or questions about this some advice here on this part of the assignment? Okay, so let's press on with, we're talking about multivariable functions. Multivariable functions. And so let's go back here. So first, here's my son, and he doesn't.
Oh my god, that's so cute.
That's not how he dresses all the time. So there's trouble with Batman, right? So there's trouble with Batman. Did you know that? Trouble, get it? So that's the game Trouble. So that's trouble with Batman. Okay. Okay. So yeah, they don't pay me for jokes. Okay. All right. So what is let's just do a little warm-up review here. We talked about single variable vector valued functions. What's that? So when you see that, what is that? What's the symbolic form? And what's the typical graph? So how do we represent those symbolically? What do we write for a single variable vector valued function?
Y equals f of x for single variable.
That'd be a single variable real valued function. Okay, good. So single variable would be like that's a single variable real valued because you're getting out a real value. But it is single variable. So what about a single variable vector valued function?
That would be 3 functions of t, right?
Right? So giving a vector, right? Giving a vector, and we usually write RT. And how does this graph? So what kind of graph do we get for this kind of function?
A curve.
Curve in space. Curve or a string of points.
Mm-hmm.
String of points. It could be linear or it could be curved. Okay? That's our single variable vector valued functions. What about a multivariable real valued function? Symbolically, how did we say that? What was that? What do I write?
Y equals f of x. C.
Okay, but yeah, we could do that. That's true. And occasionally you'll see something like that, but normally
z equals f of x, y.
Yeah, normally so. Yeah, so what you said is actually right. Y equals f of x and z. That's perfectly valid. Normally our convention is that the dependent variable is z, and we do z as a function of x and y. And how do these graph? So this is like a formula with x and y. So this is a single equation of x, y, and z, right? So multivariable or two variable real valued functions are a single equation of x, y, and z. How did we say those graph?
Surface.
Surface in R3. But then last time we saw that there was another visual way to represent these multivariable functions. Remember what that was?
Remember, did we call that a contour plot or?
Contour plot, right? Level curves. So that's an R2. So that's an R2 representation. An R2 representation of that is a contour plot or level curves. Say in. Okay, so that's just review. And we're working on these now. So we just introduced these last time. And we talked about the four different representations. A formula, a function formula, a surface in R3, a contour plot, and then a table of values. Okay, so dealing with those four different mediums, we're going to start talking about the calculus of those. And so the calculus of those will always be in one of those four, or one or more of those four kind of representations. Okay, so rate of change of multivariable functions. So think about rate of change of multivariable functions, let's start with a review of rate of change. And this may be new to some of you, that you're not really like dived into rate of change so much. It was more about like slope of the curve. And that's okay. Slope of the curve is kind of like the geometric representation of rate of change. But rate of change really applies to any quantity. And so we want to think about it not always as geometry, as slope, but as how fast a quantity is changing. And so let's see how this plays out. So here's an example. We're heading down the highway, and our phone is telling us that we're moving at 90 feet per second. Okay, that is the rate of change of distance with respect to time. So 90 feet per second is our rate of change of distance with respect to time. So what's the meaning of that number? So what's the meaning of that number 90? If it's the rate of change of distance, what does the 90 mean?
It means that you're traveling 90 feet every second.
Okay, and probably many of you are thinking that. Or something, this is a more fancy way to say it. Yeah, you're traveling 90 feet every second. Or every additional second means an additional 90 feet traveled. Okay, yeah, so every second you're going 90 feet. Okay, so what I propose to you is this is a very narrow meaning. This is in fact a very, very narrow meaning, and this number tells us a whole lot more than that. It doesn't just tell us that. It tells us a lot more. So let me show you. It tells you how fast you go in 2 seconds. How fast do you go in 2 seconds? Or sorry, far. It tells you how much distance you travel in 2 seconds, which is what?
180.
180, doesn't it? Doesn't it tell you that? Doesn't it tell you how far you go in a half a second? How far is that?
5 feet.
45.
45. It also tells you how far you go in a third of a second.
30 feet.
30.
30. And so what are these guys doing to every time to figure out how many feet you go in that amount of time? What are we doing?
You multiply the top and bottom.
You're using 90 feet per second as a ratio instead of just a quantity.
Okay. So what am I doing to my change in time to get my distance traveled? So meaning, if I had any, so really I know how far I've gone in any amount of time. How far have I gone in any amount of time? Call it dx. How far have I gone? Or will I go?
90 dx.
90 dx, right? So to answer all these questions, you just multiplied by 90, right? You multiplied the amount of time elapsed times 90, the rate of change, to get the resulting change in distance. So this number, 90 feet per second, means a lot more than just how far you go in 1 second. It tells you how far you go in any amount of time, as long as you maintain the 90 feet per second. Okay? And so that's a fuller...
It's proportional.
Yeah, exactly. It's a constant of proportionality, not just a value of distance traveled in 1 second. Exactly. So we'll sum it up this way. for any change in time. So this is the meaning of the rate of change. For any change in time, the change in distance is 90 times that change in time. Okay, so this is the broad meaning that we want to have for that rate of change, and we're going to use this. We're going to do problems. We're going to use this little equation here. It's like one of the most foundational building blocks of all of calculus is this little equation right here. Given any change in your independent, so note that this is the independent variable. X is independent. The change in the dependent is the rate times your change in independent. Okay, so just one more time, sum it all up. For any small change in seconds, or independent, the change in the number of feet is 90 times that change in time. And so we're going to need this as we start delving into these multivariable functions. We're going to hold on to this meaning for rate of change to make sense of these more complicated multivariable functions. So try to retain this. My experience teaching this to many students in many different classes is that it doesn't come super quickly and easily. So rewatch the video, rewatch this part of the video several times until you really have it down. Okay. So for a two-variable real-valued function that has the form z equals f of xy, what would we be looking, so in terms of the variables x, y, and z, we would be looking at the rate of change of what with respect to what? What?
Y with respect to Z.
So the rate of change of, so a couple of you were talking?
X and Y.
The rate of change of z with respect to x and y.
Okay, that got it, right? So we look at the rate of change of the dependent variable with respect to the independent variable. But now we have two independent variables, okay? So to keep things as simple as we can to start, we're going to take the rate of change of z with respect to x or to y. So we're going to split it apart. We're not going to mix these together. We're going to look at them separately. Okay, we're going to look at the rate of change of z with respect to x, and then separately, we're going to look at the rate of change of z with respect to y.
So are you saying that we would plug in a value for one of the variables and then change the value of the other?
Hold on to that question. Let's just hold on to the question. So I think we'll do lots that will answer that question, okay? So based on what we talked about in the previous slide, we said, so if our independent variable is x, then for any change in x, there is a rate of change that will give us the corresponding changes in z. Okay, and so that's one rate of change in this situation. And then similarly, given a change in y, there's another different rate of change that will give us change in z for that change in y. So we're going to split this apart into two exclusive separate rates of change. Both are both are looking at the change in z. One is as a result of a change in x, and the other is the result of a change in y. Okay? So this is what we call partial derivatives. That value right there is the partial derivative with respect to x. It's the constant of proportionality for changes in x to changes in z. And then this is the rate of change with respect to y. It's a different constant proportionality for changes in y to changes in z. So when we consider a partial derivative with respect to x, since we're keeping these separate, we're going to make this as easy as we can on ourselves. We don't want any influence of y. We don't want any influence of y, so we're going to keep y constant when we're analyzing changes in z with respect to x. So this implies that y is being held constant. And similarly, when we analyze changes of z with respect to y, that implies that x is held constant. Okay? So some other notation. So here's the notation function, or notation for partial derivatives. So here's the three most common for the partial derivative with respect to x. And this is a lowercase delta. Instead of English d, you use lowercase delta, and that's implying a partial derivative. You could also use partial of f if the name of the function was f. Okay? The easiest notation is just f subscript x. So that's another way to write the partial derivative of f with respect to x. Similarly, here are the same notations for the partial derivative with respect to y. Okay, so we want to start investigating, learning about these partial derivatives within the four different representations of multivariable functions. So what were those four representations? We had function definition or formula, with a surface in R3, table of values, and a contour plot. So today we're going to focus on the function definition. When we have a function, when we have the function as a formula, what will that mean for generating the partial derivatives? But then also we're going to spend some time interpreting the meaning of values of the partial derivative, because that's difficult and that's important. And then hopefully by the end, we'll see if we get time. I don't know if we'll have time to talk about partial derivatives in the mode of surfaces, but I don't think we will, but we'll do our best. All right, so function definition. So function definition, so I want to go on to this one first. So here's a cool function, multivariable function, and it gives the displacement on a guitar string at different locations on the guitar string and different times since we plucked the string. So let's draw a picture here. So here's our guitar string, it's fixed at the ends. We're gonna pluck it. We're gonna pluck it, and then at some time, we're gonna freeze, so suppose that it's gonna look like this. Okay? And so y is milliseconds since the pluck. So y is a millisecond since it's plucked, and then x is like the distance from one end. So given a value of x, we're focused on that distance. So basically this point on the string, that distance from one end. And then at y milliseconds since we plucked the string. So this thing is oscillating, right? So this is very, very exaggerated, but that's what a string does to produce the sound. It vibrates. So as it's vibrating, it's taking on these different kind of displaced positions from just at rest. So this function then tells you what? The function tells you this right there. How far the point is from its at-rest position. So this is g of xy, the displacement. Does the function make sense? So displacement, how far the point is away from its at-rest position, is a function of how far from the end you are and how many milliseconds have gone by since you plucked the string. Okay, so here's that function. So we want to look at find and interpret these values, right? So this is our function notation. This is our function notation, and these represent numbers, right? So the function notation represents certain numbers. We want to interpret what those numbers are. So this first one's the easiest. So it represents what? The displacement of the string. (70 millimeters from the end).
wouldn't it be the point on a guitar string instead of just the string though?
So that's why I said I was saying at. Yes, you're right. It's this place in the string at a point. So it's which point is it? At 70 millimeters from the end, at 2.5 milliseconds since the pluck. Hey,
keep this mute.
hey, Jonah, can you put your mute on, please? Jonah? Okay, so, and then how would we get that? Well, you just plug 70 in for X, you plug 2.5 in for Y, and you crank it out, right? So you all know how to evaluate functions. Now you just have two different variables that you're plugging in rather than one. So to get that number, you're going to plug in the 70, plug in the 2.5, and that will give you a number, and that number will mean the displacement of the string at 70 millimeters from the end, and 2.5 milliseconds since we plugged it, okay? All right, now what about this? So this takes more work and is harder to conceive, so we'll spend some time. First, we need the partial derivative with respect to x. And what did we say about y? So when you're focusing on changes of x and z, what do we say about y to make it as easy as we can?
Constant. Constant.
Hold it constant. So we're going to look at this function, and we're going to pretend that y is a constant. That's just a number. In other words, this whole thing, this sign of this value right here, this whole thing is constant. All right, so how do we handle constants? We're taking the derivative. We want the rate of change, so we're taking the derivative. And how do we handle constants that are multiplied by our function?
Leave them. They stay constant.
They stay. They come along for the ride. They don't do anything. They stay. So we have a constant of 3 times this whole sign expression that stays along for the ride. So that constant is multiplied, so we keep it, and then we're going to times the derivative of this with respect to x. So derivative of sine is?
Cosine.
Cosine. Leave the inside as it is, but then by the chain rule, we multiply by?
Pi over 100.
So there is the function, that's the partial derivative with respect to x of our guitar string function. And so, likewise, like we did before, if we want g of x of 70, 2.5, we're going to put the 70 in for x, 2.5 in for y, crank out a value. And now, this notation doesn't mean you have to do that. That's how you, if you want to get the value, that's what you do. But this notation has meaning just by itself without knowing the number, and we'll talk about that. Okay, so that's what we're going to interpret in a second. But remember, function notation.
I have a question.
Yeah.
So is g of x of y in this equation the same thing as saying dx over dz?
Yes. So that's the other. So you could say you could do this. No, not dx dz. Sorry. This. Or
Okay.
these are all notations for that same thing. So g sub x, or partial of z with respect to x, or partial of g with respect to x. Those all mean the partial derivative of our function with respect to x.
Okay, thank you.
You're welcome. Questions on finding that? Everyone see how we got that? So now we're going to do the partial with respect to y. Partial with respect to y, here we go. So now, this is constant. What about sine of pi x over 100 with respect to y? Constant. So here's where our function of y is. Everything else is multiplied, so we'll hold on to it. Constants that are multiplied stay along for the ride. Now we're doing the derivative of this with respect to y. Derivative of sine is?
Cosine.
Leave the interior as it is, but then
2 times 2.76.
chain rule, right? There's our partial with respect to y, also noted as partial of z with respect to y or partial of g with respect to y. This notation is a particular value of that we can interpret, and we will in a second. If you want to find the value of that, you simply put 70 in for x, 2.5 in for y, crank it out. If you're gonna do that, make sure your calculator is set to radians. These sine and cosines, all these sine and cosines are expecting radian measure angles. Okay, questions on finding these partial derivatives, the two partial derivatives for this function. Any questions on that? Okay, that's important, but maybe more important is interpreting these things. So I'm going to show you what the values are. So had we actually calculated those, we would have gotten these numbers. The value of the function, 1.43 millimeters, that's the displacement. Okay, so at 70 millimeters from the end of the string, at 2.5 milliseconds, that displacement right there, that little distance, is our 1.43 millimeters. Okay, what about this? So now, the partial with respect to x, which we found before, evaluated at 70 and 2.5 is negative 0.033 millimeters per millimeter. Okay, so what does that mean? First of all, what does that mean for y? What does that mean for variable y? What does the partial with respect to x mean for y?
When you move down the guitar string, that's how much the displacement changes.
Okay, good. Yeah, you're right on it. What does this mean for y?
This is like it's only true for when y is 2.5 milliseconds.
Right. So we're gonna hold y at 2.5 milliseconds. We're not gonna change y. Okay. We're gonna let x change from what? Starting at 70. We're gonna let x change from 70 to something a little bit bigger than 70. Okay, so we're gonna let x change by dx. So x is 70. It's gonna increase a little bit. What does this number tell us now? What does this number tell us?
As x increases, the distance between the string and the string oscillating in the string's original position decreases by 0.033.
Does it decrease that much? Does it decrease by that magnitude? You almost got it. It decreases by that, what?
Times dx.
Times dx, right? It's a proportionality
I
constant.
see.
You almost had it, right? So this is not the amount of decrease. It's the amount of decrease per x. So you're going to multiply that by dx to get your amount of decrease of the displacement.
So then that would basically give you how much closer it goes back to being just not vibrating anymore, right?
No, back to it's still vibrating, but back to its at-rest position.
Right. It's at position. So that's how much it's slowly stopping, and then it will come back to its. Okay.
So yeah, so what are we saying? We're saying go down the string a little bit further. I'm going to exaggerate for room's sake. I'm going to go down the string a little bit further, and what do we see about? So how much does the string get closer going down the string a little bit? How much closer does it get to its at-rest position? Well, it gets this rate of change times as much as our dx, right? So the amount that it moves closer is the rate times the little dx that we picked. So if that dx was a small value, then we wouldn't get much change in z. It'd be a shallow change. If that rate of change was a big value, then for a change in x, we'd see a big change in z. It'd be a much, the string would be, coming down a lot further, a lot faster. Okay, so holding y 2.5 milliseconds, given a change in x, the resulting change in, given a change in distance down the string, the resulting change in displacement of the string would be that rate times the change in x that we picked. That's the meaning. It's a mouthful, right? So it's a lot. There's a lot. It's wrapped up in that number, right? There's a lot of details wrapped up in that number. So we really want to work at knowing that well. Okay, questions before we go on to y. Any questions about that? So, all right. So let's do it for y then. I'll leave that up. So what does this mean? So now the rate of change of y, that second formula that we derived, evaluated at 70 and 2.5, gives us this rate of change, 5.44 millimeters per millisecond. So what would that mean? So first of all, what does that mean for our quantity or variable x, distance?
This is only true for when x is at 70 millimeters.
Right, so we're going to hold x constant at 70 millimeters. And now we're going to let what? Y change from 2.5 milliseconds to 2.5 plus dy. I'll try to make that a little smaller. Okay, that's better. So we're going to let a little time go by now. So we're going to stay at this point on the string, but we're going to let a little see a little time go by, right? And for that little amount of time, what's the displacement going to do now? Or yeah, so what do we expect? Here's our original displacement, z initial. What will we expect for the displacement now? Well, the displacement, the amount that it changes, will be 5.43 times as much as the change in time. So this told us that the displacement only decreased a little bit, right? But over time, the displacement, in the next moment of time, the displacement is shooting way up compared to that. So for the time one, the dz is positive, meaning the displacement is increasing, and increasing at a very high rate compared to how it was decreasing if we went down the string. Okay, so holding x fixed at 70, now we're fixing 70 millimeters down the string. We let y change a little bit. The resulting change in displacement will be the rate, 5.43, times the change in time that we picked. Does it make sense?
Is it like, can you plug in negative values for dx and dy, or is that not happening?
You could, and it'll work, but we usually you don't. Usually you think about, yeah, and you absolutely could, but usually you let x increase a little bit, or y increase a little bit, and that's just easier to wrap your head around. But yeah, you could absolutely, everything will be okay if you let those variables decrease a little bit. You have the same rate of change. You'll get the same. You'll get the correct change in z, because we've got positive or negatives to tell us if it's increasing or decreasing.
I have a question.
Sure.
So eventually the string is going to come back down,
right?
Uh-huh. So is that shown in our equation with dy?
No, because these are functions. Okay, this is a great question. As soon as we move away from 70 millimeters, if we make this dx too much, this is not going to work anymore. This has to be a small change. Dx has to be a small change. If you make the change too big, well, then you're messing with the rate. You're going to have a different rate of change. Say at 71 millimeters or 72 millimeters. The rate will be different. So you can't assume this anymore because you have a different rate of change. So this only works for small changes in your independent variable.
So the way that this is going to work is when you so with each variable we took the partial derivatives for say x. The way that it's going to change after 70 is by 0.033 millimeters per millimeter. So every time it changes slightly, like you go from after 1 second, for example, you have say negative. It changes by 0.033 millimeters, and then another second later by the same amount. So then it keeps going on and on like that until it gets to its equilibrium point, right?
No, it doesn't, because as soon as, so what you're talking about is changes accumulating, and so that the changes are starting to become larger now. If you have too large of a change, you get a different rate. If I plug in g, if I do g of y of 70 comma 2.8, it's a different rate of change. This doesn't hold anymore. Right? We had a formula that had x's and y's in it. If I put a different y in that formula, I'm going to get a different rate of change. These little equations are based on the rate staying constant, and that's only true for very small changes around our independent variables. As soon as you move out, say 72, 73 millimeters, or 2.8, 2.9 milliseconds, this is all off the table because you're going to have a new rate of change. Am I answering the question? Does that make sense?
So for how small of a difference does it stay?
Well, that's a relative question. That's relative to the problem.
Okay.
That depends on the second derivative. That depends on how fast the rate is changing. So they're going to be different for every problem. But in general, this will work for a small, right? So it's a very small variation in x. We can assume that variation in z will change at this rate with respect to a small variation in x. But as soon as your variation in x is too big, this is off the table because you have a different rate. So the original person who asked the question, did that answer it?
Yeah, kind of. It makes a bit of sense. It's just kind of trying to get your head.
Yeah, there's so much going right. And this is difficult, right? So there's a lot to wrap your head around. All right, let's practice some more taking derivatives symbolically using the function definition. We'll practice that. And we will practice more of this another time. Okay, where is it? Okay. Today's theme is Batman. So here's the Batman cape function up here. F of xy equals natural log 1/3 x times x minus y squared to the 1/3. So we want to find the partial with respect to x as a formula and the partial with respect to y. So looking at this, so partial with respect to x, how do we treat y? How do we treat y when we do this?
Constant.
Constant. So you got to see that minus y squared. That's the constant. So it's no different than x minus 5 or x plus 10. We're going to treat that derivative the same way as if that y squared or the y is just a constant. Okay, so how are we going to have to take the derivative? We've got natural log, we got a function of x here, and another function of x here. What does that mean for our derivative?
You would take the derivative of the natural log of 1/3 x and just leave the
We got an x over here.
I see what you mean.
So what's our structure of this going to be? What do we have to use to do this?
Use
You
the
use the product rule.
Product rule, right? So here we go. Derivative of the first. There's the derivative of the first. 1 over that times the derivative of that times the second as it is. Plus the first times the derivative of the second. So what's the derivative of that? Power rule.
1/3 x minus y squared to the negative 2/3 power
Right? But then,
times
so what's the derivative of that with respect to x? 1 minus 0, or just 1, right? When constants are added or subtracted, the rate of change is 0. The derivative is 0. When constants are multiplied, they stay along for the ride. Here's an example where a constant's being added. So its derivative with respect to x is just 0. What's the derivative of 4x plus 4? What do I do with a 4 in this case? What's the derivative of 4x?
4
4. What's the derivative of this 4?
0
0. See? When a constant is multiplied, it stays along. When a constant is added, its derivative is 0. Okay, so make sure that's the big question that students get confused with. Okay, partial with respect to y. Oh shoot, we're over. All right, but actually the quiz doesn't have an ending time, so you can take it any time. So we're gonna do a couple more examples. We still got a couple minutes, and then you can the quiz does not have a cutoff. Okay, so here we go. So now, how are we gonna approach this with respect to y? Do we need the product rule now? Do we need the product rule?
The first one, the first part's just a constant.
Yeah, with respect to y, that's just a constant. So we don't need the product rule. We just take the derivative of this. This constant stays, so we'll have natural log of 1/3 x times derivative of this now with respect to y, which is power rule, same as before, but now times what? What's the derivative of this here with respect to y?
Negative 2y.
Yep, derivative of x is 0 when it's added, minus 2y. Questions on these two? I'm going to do one more quick one before the quiz, but questions on these? So a partial derivative function is a new multivariable function derived from the original one, and it tells us rate of change. Rate of change with respect to x, rate of change with respect to y. Can I erase this? We'll do one more quick example, which will be helpful for the quiz. Okay, I'm going to erase. Back to the PowerPoint. Okay, here we go. Easier one, and then we'll take the quiz. Partial with respect to x, h of x. Derivative with respect to x. 3x squared. What's the derivative of this with respect to x?
We take the product rule.
No, don't need product rule because we just have basically a constant times x, right? We just have the constant
That's 4.
times x. And then rate of change with respect to x. 0. Partial with respect to y.
0.
The rate of change of that with respect to y is 0. Minus
8x.
8xy.
4y cubed.